Welcome to Substitution Podcast number 4. All right, so I see sine to an odd power. Pluck off 1. Sine, oops, needs to be an x though. Sine x times sine 4x dx. Pythagorean identity, we're going to replace it with a 1 minus cosine 4x. All right, so long as it's even, it's fine. Sine x, 1 minus cosine 4x dx. We're going to distribute that sine x because we're going to have to do a u to u substitution. Because if I take I can't just make u sine x, by the way, and just say, okay, I have u to the 5th, because I don't have the derivative of sine x there. That's the whole reason we plucked off, by the way, one of those sine x's and replaced the even sine x's with a 1 minus cosine x, so that I could have a sine x with the cosine x. I either need a cosine with the sine or a sine with the cosine, because when I go to take the derivative, I'm going to have, depending on which one I have, I'm going to have a sine or a cosine. So I need to have one of those in the integral. So if I just have though, I can have it if it's just to the first power. But if I've got sine or cosine, any other power, I've got to have the other one with it. So this is going to be sine x dx minus the integral of sine x cosine 4x dx. And we've seen some really similar ones to this. U here is going to be cosine x, the one with the exponent. Don't make the exponent part of it. I've done that myself on mistake and realized, whoops, I can't do that with it. I can't differentiate. So then you realize, oops, no exponent. Okay, so just remember, no exponent. Du is going to be equal, or excuse me, du dx is going to be derivative of cosine x is negative sine x. So that's negative du equals sine x dx. So now you can see I've got the u, I've got the du, and that negative is going to turn to a plus. So I've got sine x dx, that one's no problem to integrate, plus the cosine x part becomes a u, so that's u to the 4th. The sine dx becomes a du, and I've already taken care of the negative. And now I can just take the integral. I'm going to take the integral of the u to the 4th over here, so I can just write f of x after that. So this would be u to the 5th divided by 5, and that means my whole integral is f of x equals whose derivative is sine x, that would be negative cosine x. Right, because the derivative of cosine x is negative sine x, and I've got a negative there. So negative cosine x plus, and I got to replace that u with the cosine. Cosine 5x divided by 5 plus c. And we're done. It's that simple. Right? Forging ahead. Here I have 2 cosine squared 2x e to the cotangent 2x dx. And why my dx looks like it's part of the exponent, I don't know. When in doubt, try the exponent on e. U equals cotangent 2x. Right? The derivative cotangent, du dx, is going to be, why did I go to put secant? Cosecant, and of course it's negative. So it's negative cosecant blop, squared blop. Right? So it's negative cosecant squared 2x, and the derivative of the 2x part is 2. So du, and do I have all of those things before I've got everything but the negative. So the negative's not there. The 2's there. The cosecant squared 2x is there. Everything is there. So I've got negative du equals cosecant squared, and let's actually put the 2 in front. That looks weird with the 2 back there. 2 cosecant squared 2x. So I'm going to replace the exponent on the e with the u. I'm going to replace the 2 cosecant squared 2x with a negative du, and we'll integrate. And now it's going to be so super simple. It's negative e to the u du. Oh, so tough. So that's just going to be negative e to the u plus c. So hard was that to integrate. So f of x equals negative e to the cotangent 2x plus c. Couldn't have gotten easier than that, huh? That was a super simple one. What looks really complicated once you do the u to u substitution was super easy. So to use substitution to find definite integrals, you have 2 choices. Either compute the indefinite integral, expressing an antiderivative in terms of the original variable, and then evaluate the result at the original limits. In other words, substitute back, just like we did with the indefinite ones, and then plug in those very same limits that you had. Or if you don't feel like substituting back, then you have to convert the original limits to the new limits in terms of the new variable. In other words, plug those old limits into whatever u equals and get new limits. Right? So let's look at, I'm going to do both ways for all of these. Okay? And all of these are involving u to u substitutions. My u here is x squared. My du would be 2x. I have everything but the 2. So 1/2 du equals x dx. I'm fine having everything but a coefficient. The only thing I can't have is anything else. I can't be missing anything else. Right? All right, so I'm going to do it way 1, and then I'm going to do it way 2. So way 1 means I'm going to take the indefinite integral first. So the 1/2 is going to move in front. And then I'm going to have e to the u du. Right? Everything else is the x to the dx is the du part, and the e to the x squared is the u part, and I have to have the 1/2. So another easy one to integrate. This is 1/2 e to the u plus c. I should technically write the c in there, because right now it's the indefinite integral. I'm going to substitute back, however, the x squared for the u, and I'm going to put those original limits back, which means I'm going to drop the c. It's just a technicality, really. So this would be then 1/2 e to the, notice that I'm not writing f of x because this is a definite integral. It's a number. It's not a function. So 1/2, even though it looks like a function, 1/2 e to the x squared, and I'm going to integrate that from 0 to 2, which means I'm going to have 1/2 e to the, I'm going to put the 1/2 on the outside. So I have e to the 2 squared minus e to the 0 squared. All right, so that's going to be 1/2 e to the 4th minus e to the 0 squared is still e to the 0, and e to the 0 is just 1. So I can simplify that out. I'm going to leave this as the exact answer because e is just a number. So this is e to the 4th divided by 2 minus 1/2. All right, that's our exact answer. All right, let's do way 2. Way 2 is only, I'm still going to use that same u to u substitution. The only thing is since I'm going to change my old limits. So if u equals x squared, then 2 squared equals 4, and 0 squared is still going to equal 0. I'm going to have new limits, 0 to 4. All right? So all I did was I plugged in the old limits into x squared. Whatever u equals, plug it into the x for the x's, and just simplify, right? 2 squared and 0 squared. And so now I'm not going to have to substitute back, which means I don't need the c. So I still have 1/2. I still have e to the u du, but now I have limits. I have 4 and 0. And so now that's just going to be 1/2 e to the u from 4 to 0. And I'm not going to substitute back for u because I changed the limits. I'm just going to plug in. So 1/2 e to the 4th, I'll put parentheses again, minus e to the 0. And look, it's the exact same thing, right? Exact same thing. And that's because we changed our limits to match the u's from the x's we had. So e to the 4th divided by 2 minus 1/2, because e to the 0 is just 1. Same exact answers. Which way to do it? Whichever way you want. It doesn't make a difference to me. All right? I kind of like changing the limits for the u and not having to substitute back. You can see it took me just a little bit less in steps, but it's totally up to you. Maybe you think it's too hard to plug back in. I don't know. Let's look at another one here. All right, so what's my u going to be? It's going to have to be the 5 minus x, because that's a problem for me. I don't really need to do a creative u to u substitution where I rewrote x's, because I don't have an x in the numerator. I just have 5 minus x. And technically, I do have the derivative. I can do that. So if u is 5 minus x, du dx, 5, that's just going to be 0. And negative x is just going to be negative 1. I don't have a negative, but that's no problem. We'll divide both sides by negative. So negative du equals dx. See, no problem there. And behind me, if you were here for Boxer Expo, I had streamers up. Streamers are falling left and right. A streamer actually knocked over my purse. You wouldn't think a streamer would be heavy enough to do that. All right, so now I'm going to solve it both ways. I'm going to do the indefinite integral and replace, and then change the limits and not replace. So no matter what, I'll have the same equation to integrate. So negative, so this is now, my 5 minus x is in the denominator. So this is du over u. Well, what's that going to be? Well, that's going to be natural log, right? So I have negative natural log u plus c, but that c is not going to mean anything once I substitute back. The negative, you could make it 1 over u. I guess I'll simplify that because I got that negative in front there. So that'd be natural log, and I'll do that on the 5. I'll simplify and then I'll substitute just so I don't confuse anybody. So this would be 1 over u, right? Because that'd be u to the negative 1, and u to the negative 1 is 1 over u. And so when I replace, it's going to be natural log 1 over 5 minus x. And that's all because of that negative 1. That's why it's in the denominator. And remember, power rule, a negative 1 can move to an exponent. And then that would be, and then the plus c is not needed anymore because it's from 1 to 3. And now I'm just going to plug in. So natural log 1 over 5 minus 3. And then minus natural log 1 over 5 minus 1. So that's going to give me natural log 1/2 minus natural log 1/4. And I really shouldn't leave it like that. I should make it natural log of 1/2 over 1/4. This is just using the quotient rule. I really shouldn't leave it like that. That's going to be natural log 1/2. Dividing by 1/4 is the same as multiplying by 4. And I should probably put parentheses around that. So it's going to be natural log of 2. Okay? That's our final answer. All right, let's change the limits on this one. All right, so my u is 5 minus x. So if u is 5 minus x, then 5 minus 3 is 2, and 5 minus 1 is 4. All right, so now no substituting back. So, I mean, technically, I'm going to have the exact same integral, right? But I'll do it from the beginning. So we're going to have a negative du over u, and that's evaluated from, so now be careful. The 5 minus 3 means the 2 is the upper. Okay, don't just put it from, the highest number has to be on the top and the lowest number has to be on the bottom. When I substituted in the 3, I got 2. And the 3 was on the top, was the upper limit, so it has to stay the upper limit. And the 4 is now the lower limit. Okay? Well, maybe I don't like it like that. So if I switch it, it means I have to make it positive, right? The sign, I don't have to make it positive. I have to change the sign to the opposite. So if I switch the limits of integration, I have to make it I have to change the sign to the opposite. So the negative integral from 2 to 4, from 4 to 2 is the same as the positive integral from 2 to 4. So now we just integrate. We have natural log of u from 2 to 4, and hey, that's natural log of 4 minus natural log of 2. Simplify that. Natural log of 4 over 2, which is natural log of 2, like that second one. So I'm kind of a fan of just changing those limits. And if you don't like the way your limits of integration are shown, switch it. But just remember to change the sign, like I did here. I think the second way was easier on this one. All right, so let's do this one. Got a trig function. What to do with this one? Well, I don't think I want to make u cosine squared theta, because tangent's not the derivative of cosine. And I don't think I want to make it tangent cube theta. And I don't remember the answer from when I did this earlier. So what to do? Why don't I rewrite that? It's probably better if I rewrite it. It's got to be better. All right, so pi fourths 0. What if I rewrite it tangent in terms of sines and cosines? At least then I've got sines and cosines are derivatives of one another. That's better than cosines and tangents, which aren't. So this would be sine cubed theta divided by cosine cubed theta times 1 over cosine squared theta. Well, it looks maybe a little better. All right, let's make that one fraction, because I don't like it like this. Pi 0 to pi 4s. So sine cubed theta, and this would be cosine 5 theta. And I'm wondering if this is even the same way I did it in the notes, or a different way. That could be a different way. So what to do? We've got both of those raised to a power. Oh, I changed my mind. Oh, it's like I said, you could go down a wrong path and realize that's a wrong path. So it really was actually not a bad way, bad idea to do that, because I showed you now, don't do that one on this one. All of a sudden it dawned on me what to rewrite. I rewrote the wrong one. I realized that because I had, with sine raised to a power, that wasn't any better. I needed just a single sine or a single cosine, so I had a mess there. And maybe I could have rewritten that using Pythagorean identity, plucked off 2 sines. Maybe it would have worked out in the end. But I see something much more simple. Oh, I don't know why I didn't see it. I had a cosine squared theta in the denominator. 1 over cosine squared theta is, what did I put sign? Is secant squared theta. My hand wasn't listening to what my brain is saying. Now, that's much easier. Pi to the 4th, 0, tangent cubed theta, secant squared theta. Now I've got a function in its derivative. So, moral of the story, don't always replace tangents with sines and cosines. Sometimes you want to go the other way. So, remember that 1 over cosine is secant squared theta, and now we're all good. What's my u going to be? Just the tangent theta, not the cube. That'll be a problem. I'm not making a second mistake. du dx, therefore, is going to be secant squared theta. So du is secant squared theta d theta, or dx, excuse me. So you were probably, oh wait, it should be d theta. Sorry, it's not with respect to x. We did so many dx's. This time it's respect to d theta. And so you probably have it, you may have done this, had this done in your notes already for you, and you're probably thinking, what is Miss Michelle doing? She's going the wrong way. But I fixed it in the long run. All right, so, and this goes to show you that if you start to see you have made a mistake and you don't have a function in its derivative, abandon it and try something new. And this was our something new, and this is a good something. All right, so everybody is covered here. The only thing I'm keeping is I'm keeping the cube. So, and we'll evaluate this both, evaluate this both ways. No limits of integration right now. We've got the integral of u cubed du, and that's just going to be u to the 4th divided by 4 plus c, which I'm going to drop in a second. So now I'm going to substitute back. That's going to be, u was the tangent theta, so this is going to be tangent 4 theta divided by 4, evaluated from pi fourths, or excuse me, 0 to pi fourths. All right, so I'm just going to put the 1/4 in front. 1/4, so I've got tangent pi fourths minus tangent to the 4th power 0. So that's 1/4. All right, so all right, there's 1 pi fourths. That's the 45, 45, 90. So 1 square root of 2. So that's just going to be 1, right? It's 1 over 1, opposite over adjacent. So I've got, and 1 to the 4th power, right? Because that whole thing is raised to the 4th power. And then minus tangent 0 is 0. So I've got 0 to the 4th power. So what I've got is 1/4. Right? That's the area, the definite integral represents the area under the curve. All right, let's do the same thing, but this time we're going to change the limits of integration. All right, so if u is tangent theta, right, then tangent 0 is 0, and tangent pi fourths is 1. So now I'm just going to have the integral from 0 to 1 of u cubed du. So that would be u to the 4th divided by 4 from 0 to 1. Gee whiz, that's just going to be 1 to the 4th power divided by 4 minus 0 to the 4th power divided by 4. That's 1/4. So see, really, really simple, I think, on the changing your limits. And our answers match. Getting close to my 30-minute mark. It looks like I'm just about done. All right, so method of substitution was a homework for you. So definite integral, when you got your limits of integration, that's a definite integral. If you have an indefinite integral, it's a summation. It's the limit of the Riemann sums as the number of rectangles goes to infinity, or the change in x goes to 0. the dx there is your variable of integration, and then this is your integration symbol, gives you the family of functions who has f of x as the derivative. This is the sloppiest handwriting I've ever seen. Ugh. But it's got a lot of good information, and I think I put it in your notes as this anyway. So if you got to look at the sloppy handwriting in your notes, you may as well have to look at the sloppy handwriting on this podcast as well. So we have very different things when we're finding the indefinite integral, and the definite is the, either way it's a summation, but your definite integral matches up to the limit of Riemann sums. I don't think I made that clear on this at all. Let me make this clear, which goes with which. Because I just read this as I went down the slide, and I'm like, gee, I don't have these matched up well. So let me review. When we have a definite integral, that's the limit of the Riemann sums as n goes to infinity, change in x goes to 0, right? It's the area under the curve. It is a number. The indefinite integral, boy, not only is it sloppy, it's not well organized. Now these arrows will help. Add these arrows. I wrote this earlier, and not in the neatest way. So, definite integral, limit of the Riemann sums, area under the curve, using our geometric shapes, that's all the same thing. It's a number. Okay? Indefinite integral, both of them, by the way, are summations, but indefinite integral, excuse me, really the summation is this. Well, we have the S indicating summation, but when we really think of summation, we're thinking of this, and we're thinking of the definite integral, quite honestly. When we're thinking of the indefinite integral, we're thinking of the family of functions who has f of x as the derivative. We're really thinking of the antiderivative. All right, so kind of two separate issues there. Okay? And I hope that's clear. And if not, I'll make it clear in class. And I think that's the end of this. This I'm going to do in class at a later point, and that's the end of my podcast here. The only thing I have to go back to is those inverse trig ones, but I don't know that I'm going to do that tonight. You may watch that on Monday night because I think I'm done. All right, so see you for now, and see you later. And you can see I'm done. Bye.